As I said, our aim is to find out the field equation using Lagrange formulation. Okay, in classical mechanics, the Hamilton's variation principle gives the necessary and sufficient condition for formulating equations of motion. We know already about the Hamiltonian variation principle will bring out the equation of motion. We know already. So this is your variation principle. So delta variation, this is your delta variation of action of a distance which is equal to 0. What does it mean? Delta variation of Lagrangian which depends on time which is equal to 0. So this will be your extremum condition, minimum condition. About path integral, can you remember path? So action at a distance, and provided this condition should be satisfied. Provided this condition says that virtual displacements, so this is about virtual displacements, that is positions are the same at n points. Look at this one, this is your initial point, this is your final point, and both are n points, initial point and final points, they are the same, that is equal to 0. So if this condition is satisfied, we will have to have this condition too. Okay, so here L is a function of psi comma psi dot. Lagrangian depends on psi comma psi dot. So Lagrangian means L stands for Lagrangian of the field. So now we are going to introduce Lagrangian density. So in some other book you may find curly L like this. In some other book you may find L like this. In some I have written as L bar. L bar stands for Lagrangian density, which is nothing but Lagrangian, the values of Lagrangian per unit volume. So per unit volume. So Lagrangian per unit volume, which is nothing but your L bar. So L bar, which depends on psi, comma del psi, comma psi dot, comma t. So as I said, 4 functions are there, 4 vectors are there. Don't forget. So they are all dependent. So this is position dependent. This is time dependent. Okay. So psi, comma d psi by dx. This will be d psi by dt, comma t. So of course this is continuous dependence of psi on r. Lagrangian density depends on r comma t through psi of r comma t. And we know that the field exists everywhere. Suppose if you are going to consider the field like this, so in which we have a volume. If you are going to take a small cube and we can consider this as a volume as dV, so in which the Lagrangian density can be written as dl by dV. So already we defined that Lagrangian per unit volume is nothing but Lagrangian density, correct? So Lagrangian density is nothing but dl by dV. It's very simple logic. Okay, so dl equals cross multiplying will give you Lagrangian density multiplied by dV. So integrating on both sides will give you this equation 10.5. Is it okay? So Lagrangian is equal to integration of Lagrangian density multiplied by dV. Thus Lagrangian L of the field would be integral of L bar over the space. If you want to have a continuous over the space, we will have to integrate over the space. Total Lagrangian of the field is given by. Now we know that L equals L bar is nothing but this one. So you just a substitute here. Correct? So I repeat, L equals L bar dV. L bar is nothing but this one. Already we have seen in the earlier slide. So your L bar, we are going to substitute for L bar, we will have this one. Instead of dV, you can substitute for dq bar. The Hamiltonian variation principle, which corresponds to equation 10.3 is now we will have to use this Hamiltonian variation principle, which is nothing but del variation with L dt. Instead of L, you can substitute this one. Already one integral is there. We have another integral is there. This integral with respect to t. This integral with respect to position. So we have two integrals now. One is for position, another one is for time. So one is for position, another one is for time. And of course, instead of L, we can substitute all those things. Is it okay? So now I can bring this del inside. We can write this as del Lagrangian density, d cube r dt. So we have two integrals, which is equal to 0. Is it okay? Where the small variation del psi of psi is subject to the condition. This condition should be satisfied. We are going to discuss. If this is so, and this must be true. Okay, so this is for the mechanical system and this is for the fields. This is for the mechanical system and this is for the fields. Any doubt? Okay. So it says that see, virtual displacement position are the same at the 2 points. It will have the same answer. Okay, now we are going to differentiate equation 10.4. So 10.4 is here, we are going to differentiate. And of course, L depends on four functions are there. Okay, so we'll have to go only with the partial differentiation, no other way. So more than 1, 2, 3 means we'll have to go only with the partial differentiation, more than 1. So here it is 4 functions are there. So we'll have to go only with the partial differentiation, which is nothing but your del L. We are going to differentiate, okay, del L, which is equal to del L bar. First we will go with the psi. So partial del L by del psi, okay. Partial dl by d psi, del psi, plus partial dl by d del psi, okay. So similarly we can go for psi dot. So partial dl by d psi dot, del psi dot, plus the last one variable will be your t. So partial del L, so partial dl by dt del t. Any doubt? So we have 4 variables. So we will have to use only partial rules, partial differentiation rule. So this is partial differentiation rule. Any doubt? And as I said just now, we have del psi stands for d psi by dx. And of course we have 3 coordinates. So we can write, instead of this we can write a summation over x, y, z. So this stands for d psi by dx. Del psi equals d psi by dx. It means d psi by dx plus d psi by dy plus d psi by dz. So we have first term, second term, third term and fourth term. So here the summation over x, y, z implies that the sum of 3 terms with y and z, okay, substitute for x. So instead of x you can substitute for y, instead of y you can substitute for z, that's all. Is it okay? Now we will take this term alone. Del d psi by dx. Del partial d psi by dx. We can replace this as exactly this expression. D by dx, partial d by dx, del psi. Similarly, you go for del psi dot. Del psi dot can be written as del psi dot is nothing but d psi by dt. We have already seen earlier. So this can be written as partial d by dt with del psi. So we are going to replace this expression by this expression by this in the next equation. Any doubt? Very simple. So this equation 10.10 reduces to. So we have replaced now. We have replaced this and this. Can you remember? We have replaced this expression and we have replaced this expression too. Now substitute equation 10.12 in 10.7. 10.7 is here. So we will have to substitute 10.7. So we will have 2 integration, one with respect to position, space, another one with respect to time. So one is with the volume, space coordinate, another one with respect to time. And this is expression for your del L. See, total del L is given by this expression. So total del L is here. And integrating with respect to space and t, so d cube r dt which is equal to 0. Using this equation, we can write, instead of this del L, you can write all those expressions and get the equation 10.13. Any doubt? And what is the last one? Last one is with respect to t. Correct? So we have t1 to t2 dl bar by dt, partial dl by dt, del t dt equal to 0 because initial and final points are the same. We have already written the condition. So initial and final points should be same. So this must be equal to 0. So what are the values for initial? The same values also will be at the final. So if you subtract it, it will become 0. So the last term will become 0. Now we are going to only 3 terms only. So hence equation 10.13 becomes the first term, second term, third term. Now we are going to solve for second term and we are going to solve for third term. Substitute here and get the field equation, Lagrangian field equation, Euler Lagrangian field equation. Now first we will take second term. We are going to integrate by parts. We are going to integrate by parts with respect to space coordinate, because this is related with the space coordinate. Okay, so with respect to space coordinate as, so just take the second term. So we are going to take the second term and we are going to keep this as u, we are going to keep this as dv. So we know that integration of u dv equals uv minus v du, we know already. So we are going to integrate this one by integration by parts. So we are going to consider this as u, as I said, the whole term as dv. So which is equal to uv, we can write this as u. What is v? We just cancel this one, you will get a del psi, that's all. So you have del psi and this is your u, okay, minus v du, minus integration over v, your v, already we have obtained v is nothing but your del psi, so del psi is here. What of du? We will have to differentiate with respect to x, so d by dx of this u term, very simple, and this becomes 0 because psi disappears at when x tends to 0, when y tends to 0, when z tends to 0, or when r tends to, not tends to infinity. Okay, psi disappears, psi will vanish at r tends to infinity. So this term will become 0. So we are going to have this term. Instead of this term, second term, we can substitute this term. Is it okay? Simple idea. Similarly, we are going to have now third term. We are going to have an integration by parts. As I said, this is your second term expression. Okay. So just take the third term now. Again, you are going to use integration by parts. We are going to integrate. So this is your third term. And you are going to consider this as u. You are going to consider this as dv. What is u? U is here. What is v? Without this term. So this become del psi. So this is your u and this is your v, uv, minus your v du. Similar argument. So your v will be del psi, we written your du, your u is here, du is nothing but, now with respect to time, see, look at the with respect to time. Earlier it was with respect to position coordinate, space coordinate, now with respect to time. So this becomes d by dt. Okay, very simple. So now this third term can be replaced with this term because this will become 0. Same argument. Okay, implementing equation 10.8, equation 10.18, third term becomes 0. Okay, so this term becomes 0, you will have third term becomes exactly like this with a minus sign. Any doubt? The same argument in the sense, as I said, t1 and t2, at both the end points the answers will be the same according to this. Both the end points answers will be the same. You have a values at initial point, you will have the same value at the final point. So if you substitute t1 and t2 according to this condition, this will become 0. So you will have only this expression is exactly equal to this. So we have third term, expression for third term is given by this. Okay, now again we are going to substitute. We will substitute. So this is your first term, we have not disturbed anything. Second term we have replaced with the integration by parts. Third term also we have replaced it with the integration of by parts, which is equal to 0. Is it okay? Any doubt? Very simple one. Now we can simplify exactly this as exactly like this. We have kept the integration dt, d cube front side, and you are keeping del psi as common out, we have taken del psi out. The same equation, we have kept del psi common out. See, del psi common out. And out this equation says that del psi cannot be equal to 0. Okay, this can be equal to 0 because something is equal to 0. The argument goes like this: del psi cannot be equal to 0, and this term will be equal to 0 because del psi is not equal to 0 means psi is, it is an arbitrary. Arbitrary means psi 1, psi 2, psi 3, they are all independent. So they cannot be equal to 0. So this integrand should be equal to 0. So if it is equal to 0, we will have this equation. This equation is known as Euler Lagrangian equation. We have used L bar. Don't forget, this is Lagrangian density. In ordinary classical Lagrangian equation, we have used only L, but here we have used Lagrangian density. There it is, simply it is L, Lagrangian. So values of Lagrangian per unit volume is nothing but Lagrangian density. So this equation is known as Euler Lagrangian equation. This is one field equation. We have found out one field equation. Okay, now we are going to compare this and that. So this is from field equation, quantum field theory. We have used psi. Psi is a function of r comma t. Okay, here it is q and q dot. Okay, this is for the classical equation, and this is for the quantum field theory. We have used only psi, amplitude, field function. Now we have just to compare these two. We are going to compare. Okay. So when you are going to compare this equation, we can say that before that. Okay, we can say that, look at this. This is Euler Lagrangian equation, in which we have three terms: the first term, second term, and third term. Okay, this is first term, second term, third term. And look at the second term. We can separate into x coordinate, y coordinate, z coordinate. Okay, x, y, z. We can write in terms of covariant form. Can you remember, we studied in the last minute, covariant form. X dx mu. So mu stands for 1, 2, 3, 4. 1 stands for x, 2 stands for y, 3 stands for z, 4 stands for your t, time coordinate, ICT. Very good. So mu equals 1, 2, 3, 4. So 4 coordinate system. In classical physics, L is a function of q comma p comma t. Sometimes if it is t is independent, then we can write q comma p. So q is independent of p. Whereas in quantum field theory, L is a function of L bar. Lagrangian density is function of psi, del psi, psi dot, and t. So 4 coordinates. So we have 4 derivatives, all derivatives. So that's why some extra term has come. See, extra term. Here there is no extra term. Only we have only 2 terms. Suppose if this term is not there, both resemble the same thing. Okay, so that's just a comparison. Here q and q dot, they are independent. Here they depend on each other. So that's why we have extra term. Exactly resembles with the classical field equation, classical equation. Okay, any doubt? So in this class, we started with first quantization, the difference between first and second quantization, which are very important when you are talking about second quantization, and especially on quantum field theory. So fields are very important. Okay, fields are nothing but waves. So we know already. Okay, infinite number of degrees of freedom, that will give us infinite number of particles. So waves will be there, fields will be there, everywhere it will spread, having infinite number of particles. So out of field equations, we have studied only Lagrangian, Euler Lagrangian equation. Okay, so we'll start today. We'll discuss the next part in the next class. Okay, bye students.